Welcome everybody. In this video, we're going to do a full example of computing the Fourier series and all its coefficients for, well, this particular function, what we often call the sawtooth wave. Now, if you have no idea what a Fourier series, that's totally okay. Go down to the description and you can see my introduction to the big idea of Fourier series. And this is just going to be an example where we actually compute it all out in an explicit case. Now, the function that I'm going to study is called the sawtooth wave, and you can sort of visually see why. It's the function f of t equal to t, but it is only f of t equal to t between -2 and +2. And then beyond that, outside of that interval, it extends periodically. It's kind of like another copy of the same graph between 2 and 6, and then 6 and 10, and so on and so on. Just periodically doing the exact same thing. Also worth noting, this is a discontinuous periodic function, and indeed, Fourier series are going to be able to handle that very well. Now, to figure out the Fourier series, I've written down already the general formula for a Fourier series. It's a sum of sine terms, cos terms, and one constant term out the front. And our real question is, what is the a0, what is the an, and what are the bn? That's what we want to compute. Now, the first distinction I'm going to make compared to my previous example is that this is going between -2 and 2. And you'll notice that in the general formula, there's a location of L. And so basically this is saying that L is equal to 2, and I'm going to plug it in at those two different spots. All right, now the next thing I want to do is try to write down the formulas for the coefficients. And the first one I'm going to do is write down the formula for actually the an. And the formula goes as this. It's 1 divided by L, which in this case is the value of 2. The integral between -L and plus L, which is -2 up to 2. And then for the integrand, I put first the function, which in our case is going to be t. So this is the specific function that we have for our specific example. And then multiplied by cosine of n pi t divided out by 2 dt. Now, do I need to evaluate this integral? In fact, I do not. There is a nice little trick that allows us to immediately see that it is always going to be 0. So why do I think this? Well, the argument is as follows. If I look at what cosine is, this is what we refer to as an even function. What I mean by this is if I was to write cosine of negative any value, perhaps say x, it's just the same thing as cosine of x. As in, if you put in the negative, you get exactly the same thing. Okay, so cosine is going to be an even function. But what about t? This one is going to be what's referred to as an odd function. An odd function is one where if you put in a negative value, then what you get is the negative of the function. And indeed, this is the case for f of t equal to t. And so then collectively, when I multiply the two of them, what I get is an odd function. As an odd function times an even function gives you an odd function. If you put in negative a, then you're going to get negative whatever you would have gotten with just putting in the value of a. This is an odd function. And because it is an odd function on a symmetric interval, basically what this means is that between -2 and 0, all of the values are just the negative of what they are between 0 and 2. It's an odd function. Over a symmetric interval, it always cancels out exactly. So I don't have to worry about it. It's just always equal to 0. I'm not going to bother doing any integration by parts. I can actually do the same argument for the a0. So how does the a0 work? a0, again, is 1 over 2, the integral from -2 up to 2. It's a simpler function, t times 1 dt. I mean, this is actually easier to see. Again, it's an odd integrand. It's an easier one to do, t squared divided by 2, and you can plug in 2 and -2, and indeed they cancel. This one is also going to be exactly to 0. But I don't even need to do the integral. I immediately look at that integrand, I say odd integrand, symmetric interval, it's going to be 0. Okay, well, maybe everything's going to be 0, but, well, let's be a little bit more careful. Let's look at what our bn is going to be next. So 1 over L, which is 2, -2 up to 2, our function, which is t, but now sine of n pi t divided by 2 dt. Now I can't do the same trick. Sine is an odd function. Sine of -x is the negative of sine of x. T is an odd function, and odd times an odd function is an even function here. So this is an even function. So this doesn't cancel out to 0 because that same trick doesn't apply, but a slightly different trick does apply. If I think about what happens between -2 and 0, if I plug in any t value in between there, it gives me the exact same value as if I didn't have the negative. So there's sort of a doubling that happens when I have an even function. So what I'm going to do is I'm going to erase the bottom limit of integration from -2 and replace it with 0. And then I'm going to multiply the whole thing by 2 out the front. And the basic just argument here is that this even function is kind of like just take half of the interval and double it. An odd function is like the two sides have the opposite sign and so they cancel to 0. Okay, well, I'm out of tricks. I guess I just have to do this integral now. There's nothing else. So what can I do? Well, it's a product of two things. So integration by parts. Come along here, that's my u, and all of that is going to be my dv. With that analysis, I'll say that du is just going to be equal to dt. And likewise, if I want to write what the v is going to be, well, this is sine turns into cosine, but it needs a minus sign. So -2 over n pi cosine of n pi t divided out by 2. There we go. All right, so I now just need to plug all of this in. The 2's cancel out the front, so I don't have to worry about any of that. I'll do my u times v, so this is going to be -2t divided by n pi times cosine of n pi t divided by 2 and evaluated between 0 and 2. I then subtract a negative, so that's going to be a plus. The integral from 0 up to 2 of 2 divided by n pi, again I've already dealt with the minus sign, cosine n pi over 2 times t integrated dt. Okay, so what can I do here? I have another integral. Do I have to evaluate that? Well, I do not. Again, I do not. If I think about what the graph is, here, let me give it a little bit more space. If I think for just a moment about what the graph of cosine is, there is the graph of cosine between 0 and pi. Our specific example has this stretching factor of pi divided by 2 there, but that doesn't matter. It's the same argument. If I'm looking at what cosine does, well, it's half positive and half negative on that interval. If my n was larger, then it would just do more, right? This, for example, would be the fact if it was n equal to 2 or n is equal to 3, it would keep on coming down. But it always has that property. So anyways, this entire integral just goes to 0. Indeed, whenever you do integrals with coses and sines, I like to sketch out a quick graph, just make sure that I'm correct, and then I just apply the identity that I do, and a lot of these things are going to be 0. I love doing integrals with cosine and sine for that reason. It just all simplifies. All right, so that leaves me with what I have over here. Okay, so if I plug in the value of 2, then I'm going to get -4 over n pi. And then I'm going to have cosine of n pi. And cosine of n pi is something we've studied before. So maybe I'll write it explicitly. Cosine of n pi. And then I indeed am also going to have to subtract off 0, but subtracting off the 0 is just going to give 0 because t equal to 0 at the front. Either way, what's this? Well, cosine of np goes between, if n is equal to 0, 1, -1, 1, -1, 1, -1, and so forth. So this is just -4 over n pi. It is -1 to the power of n. And if you prefer, I'll erase the 1 minus sign and I'm going to put it up here. I'll make it n plus 1 just to put all those minus signs together. So that's my coefficients. And now I'm ready to state my final answer. So this is my formula for the Bn. So what is my f of t? My f of t is a sum. It only is going to include these sine terms. There is no a0 term, there is no an terms, there's only bn terms. And so what do I have? 4 divided by n pi -1 to the power of n plus 1, all multiplied by sine of n pi t divided by L. That is my final answer for the Fourier series of this particular sawtooth wave. All right, I hope you enjoyed this video. If you did, please give it a like for the YouTube algorithm. Coming up in the next video, we're going to see, it's one of my favorite ones. We're going to see the linear algebra perspective of Fourier series.